Is my voice audible? Can anyone confirm whether my voice is audible? Okay. So few others have to join, but we'll start. We have waited for 5 minutes. Okay. So this will be the last session for a lab. Okay. So this is the fifth session. We'll be completing a binary search tree in this session. And tomorrow, as I already mentioned, the schedule that will be an internal assessment that will be spread over 2 days actually. Uh, I think just like your CPNM lab, you had one day for records and observation on Monday, and on Tuesday, I think you had an exam. So I think, were you given any schedule? Can anyone confirm whether you're given any schedule? So when is the date, last date? When is the date for record submission? Uh, Internal exam? Were you given any dates for data structures lab? Does anybody have the schedule? Because I have schedule only till tomorrow, that is Saturday. The dates for record submission and internal exam, those dates are not yet available with me. Were you given any schedule? No idea? Nobody? Okay, we'll see. September 9th is last. So is there any date-wise schedule given for all batches for different branches? I think there'll be one sheet. I saw that sheet for CPNM, but for data structures, I have not yet seen that schedule. What is September 9th last means? Is the 9th last for class, or that includes the exam? Are your dates for your first semester exams released? Semester exams for additional works, okay. When are your exams starting? Semester exams, first semester? Theory exams, theory. Are your dates not yet released for your first semester exams, theory exams? 27th. Okay. Okay, fine. Okay, then we'll see. I'll just find out what is the schedule. But assuming it will be similar to the schedule like CPNM lab after the last class, that is tomorrow. Monday there'll be a one day allotted for record submission and assignments. That's your observation and record. And Tuesday, that will be the exam. So I'll find out whether it is similar here also. But anyway, today there will be the last class for our programming part. So tomorrow there will be an internal exam. I asked you in the last class whether uh, is there any need to postpone it on Sunday, or are you ready for tomorrow? Nobody has informed me yet. So in that case, we'll be having it tomorrow. Okay. So it will be spread over 2 days. One tomorrow and one some other day, whenever the university tells. Okay. So that will be one on Viva and one will the programming part. You have to write the program and execution. That is one day. Viva will be on another day, whichever date the university suggests. Okay. Okay. Anyway, that we'll discuss later. So coming to today's session, before we start today's session, yesterday in the last class, we were unable to take the 3 hour session in the morning. So I have taken the class in the evening. So because you had other works, record work and all, I just left you early. Okay, so I was trying to complete a bit fast. So I'll just repeat what I have told in the last, towards the end of the session. I think we were discussing about double-ended queue. So briefly in 5 minutes, we will review the topic that is double-ended queue that was discussed towards the end of last session. And then we'll continue with today's session, okay? Okay, so in double-ended queue we were discussing, it will have four functions. Okay, four functions. So double-ended queue is something where the insertion and deletion can happen at both ends. Unlike a regular queue, the insertion happens only towards the rear, and the decay operation, that is removal, happens from the front. Okay, but double-ended queue, as the name suggests, both insertion and deletion can happen from either end. Okay, so obviously we'll be having four functions: insertion at the front and insertion at the rear, deletion from the front and deletion from the rear. So it will code up four functions, and we're seeing this. The code is a bit lengthy. We've seen that. But I told you the logic is very simple. So I think this we are discussing towards there. So let us once again review. Okay, so this will be a queue. Okay, and this will be, say for example, we're right now here front, and maybe there's more space here, and maybe somewhere here we are right now rear. So we have, if you want to insert, this insertion can happen either here, okay, or here it can happen, the next empty space. So two options for insertion. Okay, and similarly you can delete from here if you want, from here also. Okay, so two options for deletion. Okay, so these are the functions we are coding. Okay, so let us see how to code up. So insertion at front, and then we have insertion, this will be at rear. Okay, similarly deletion at front and deletion at rear. Okay, so what I told you was there will be two cases always you have to consider for each of these four when you're writing code for it. Okay, there will be two cases. One is the normal case. Okay, so always remember the normal case and the special case. The normal case is when the queue is partially filled. Okay, there are some elements. Okay, the elements are not towards the end. Okay, there is still space towards the end. So this is a normal nice case. So in a nice case, if you want to insert at the front, say for example there are three elements in the queue, and there is still space towards the end and towards the rear and the front, everywhere. Only three elements are there right now. If you want to insert at the front, so front is right now pointing here, a new element will come here. Okay, so this will be the now the front element. So you have to move front here. Okay, so always when you're writing code for double-ended queue, just imagine in your head a figure with two cases. One is the normal case and the special case. So normal case, here we have space. So all you need to do in insertion at front is when the new element comes here, the front pointer will be moving to the left. That is, front is equal to front minus 1. Okay, so insertion will be front is equal to front minus 1. That is insertion at the front. If it is insertion at the rear, what we do? Say for example, this is the last element, and now you have space, still space, and if you want to insert, okay, if you want to insert at the rear, this will be rear is equal to rear plus 1. Okay, this is the nice cases. Simply you can directly write. Similarly, deletion from the front. Okay, so if this is the element, you want to delete this element, then this becomes the new front element. Okay, so then front will be front plus 1, and similarly deletion from the rear. If this is the last element, you're deleting it. Now this will be the rear element. So rear will be rear minus 1. Okay, so these are the simple conditions. Okay, provided there are some elements already. But sometimes the special case will be like, say for example, you're trying to insert at the front. Okay, and there's already an element at the front. This is the first index, starting index. This is already an element. This is the last, the maximum size and minus 1. So now you're trying to insert the front. It's not possible to insert at the front because there is no more space. Okay, so actually this is like a circular. You have to think like this. Okay, though this is not how it is internally, the memory allocations are just series of blocks. Okay, there is no a circle inside, but you can think of it like this. Okay, so starting at index 1, you go 2, 3, 4, and after index n minus 1, you come back here. This is how the circular queue and the double-ended queue works. After reaching the end, you come back here, provided that this space. So this actually will loop back here. Okay, so even though that is not entirely correct, conceptually you can think it like this. Okay, after n minus 1, you come back here. So when you're trying to insert at the front here, and already you're at the end element, what you do? Normally you have to do front minus 1, but you get an error because array, the index is 0, there is no space. Then you have to go back here like this. Okay, you have to go here. So here you have to go like this. So this is the case where you're already at the end. Then this is the special case, that is you check it whether front is 0, and then if front is 0, what to do, you have to make it the maximum, whatever max size minus 1. So take it here. This is a special case you have to take care in every condition. For example, you want to insert it the rear. Normally you will be able to do rear plus 1. But for example, you are at this point and now you want to insert the rear. You already reached the maximum error size. Now you cannot insert. What you do? You go back to index 0. Okay, so go back to index 0. So here again you have to check whether if rear is equal to the maximum size, then you have to make it to 0. Similarly, deletion from the front. Okay, deletion from the front, you can add up 1. Okay, so deletion from this will make the next element, you can increment 1, but provided there is space. Okay, say for example you are hit the last index, front cannot increment, then make front 0. That is if front is hitting the maximum size minus 1. And similarly, deletion from the rear, you can move back, increment, you can decrement rear by 1 point, provided you have not hit this index 0. Then in which case, if rear is 0, then make rear the maximum size minus 1. Okay, so these are the 8 conditions you need to take care of. Okay, in addition to these conditions, at every stage, for example, for insertion, you have to first of all check whether the queue is full or not. Okay, so that anyway you have to check, is the queue full or not, because if it is full anyway you cannot insert. That you have to check. For deletion you have to check whether it is empty or not. If it is empty, you cannot, there are no elements to delete. Okay, this you have to anyway check. Okay, so is empty means you just check whether front is equal to minus 1. That is the condition to check whether the queue is empty. And whether full or not, I think we have already discussed. So full arises in 2 cases. Okay, so all elements are filled here completely. Okay, so front is pointing here, rear is pointing here. So front is equal to 0 and rear is equal to size minus 1 is one case. Okay, but there could also be another case where we're discussing this implementation, right, in circular. So after filling here, so normally what happens, rear will be ahead of front, but in the special case we'll also find a situation where front will be ahead by rear plus 1. So this is the end. One more condition we check for whether the queue is full or not. Okay, so this is how you have to write. The code will be lengthy just because the conditions are more. Okay, there are 4 functions, and for each of the 4 functions you have to write 2 conditions apart from checking is full or is empty. Okay, so these are the so many conditions are there, total 12 conditions. Okay, for each of the 4 you have to write 2, that is total 8. Then for each of this is full or is empty plus 4, totally 12 conditions you have to check in double-ended queue. That is what makes the code lengthy. Okay, but conceptually it's very simple. Okay, so if you have time you have to go through once again this code. Okay, but the conditions are very simple. Okay, if you see the handout, for each function, say for example insertion at front, you'll check whether the queue is full or not using the isFull helper function. That's already defined here. Okay, then this condition, normally front plus 1, but you have to reinitialize in case you're unable to move that. Okay, so these 4 functions you have to be clear. Double-ended queue is actually a difficult program. If you get this in exam, you should be unlucky because its length is more. Otherwise, the concept is very simple. Okay, so that is regarding double-ended queue. Any doubts? Double-ended queue programming part. Okay, it might take some time for you to understand, but at least the theory part, are you clear what we are doing? Okay, Mahendra says rear is equal to rear plus 1 must be answer to some question. I didn't see this. Okay, fine. Okay, so is the theory portion clear? Double-ended queue. Okay, so then we'll proceed with today's session, and today's the last topic for the course is binary search tree. So in your lab syllabus you also have topics on sorting, 3 sortings: merge sort, quick sort, and heap sort. But we are not covering them in your syllabus because I think for your theory course it's only 70% syllabus, so maybe sorting and graphs, the last 2 units may not be discussed, I'm not sure. But even then we'll be ending the session for a lab course with binary search tree. will not be coding. In today's class, I will definitely discuss the overview of sorting. The three sorting methods I will discuss, but that's only for your understanding, just to have a complete coverage of data structures lab syllabus. For your exam, I will not be asking the sorting and graphs. Okay, so till binary search tree will be the coding part, but I'll also discuss the theory portion for the three sorting techniques: merge sort, quick sort, and heap sort. Okay, so let us start with binary search tree. So I think this also you must be covering this in your theory class. I think this is the topic right now you are discussing: binary search tree and traversals in order, pre-order, and post-order. So is this topic covered already? Are you still in this unit, binary search tree? Are traversals completed in order, pre-order, post-order? So are you aware of the traversal methods and binary search trees, or are you still in the unit covering the topics? Is that unit completed? You're still in the topic. Okay, so you're going through. So are the traversal methods completed in order, pre-order, post-order? Those topics. Okay. Okay. So in this session, we'll see how to code up the binary search tree. And again, the topics which we have been learning from the very first session, that is recursion and pointers. Again, those the topics will be revisiting us today. Okay, so from the beginning, I'm telling you, you need to be very strong in linked list, that is pointers and recursion. Two topics extremely useful for data structures lab. Again, for this course today, that is the binary search tree, we'll be making use of recursion and pointers. Okay, so let us see. Okay, this code I'll just copy. Not now, I'll just implement it after discussing. But this is the code for today's session. Okay, so I think before that, a couple of announcements. I think I've already told you. I think I discussed in the last class itself. Assignment 1 is already graded. I think the scores are already available. Uh, I also told you that I'll be regrading it, scaling it towards 10 marks, even though it's for 40 marks. But even if you got less marks, don't worry. Okay, we'll adjust it later. That's not a problem. Okay, and solutions also have posted a separate video in case you're interested. You can watch the solutions. And assignment 2 will be released by the end of today's class. Okay, by the end of today's class, that should be available on Canvas. And the due date is tomorrow, because tomorrow will be the internal assessment, just one day. So because of the time constraint, I have made it very simple, only 10 questions. All are multiple choice, no theory questions, and it should not take more than 5 minutes. If you are listening to the class on today's class, and if you had listened to the previous class and cues, straight away you can take this quiz. Nothing complicated. Everything what we have discussed in the course. Okay, nothing difficult. Everything what we have discussed in the class will be asked. All are multiple choice, just 10 questions. So try to complete it by today itself. Okay, don't prepare too much for this. Okay, this should be an easy quiz. Okay, only the weightage is 5 marks. The questions are, even though for 10 marks, I'll be scaling it to 5 marks. So assignment 1 is 10 marks, assignment 2 is 5 marks. Okay, so 15 marks will be completed today. And I already told you regarding tomorrow, there'll be an internal assessment. Okay, so in case you want it to be moved to Sunday, that then you have to inform me. Okay, otherwise, if you're fine with tomorrow, we'll go ahead. So as I told you, the internal assessment will be for the program. You'll be given a program and you write the code and execution. So uh, you might get any one of the programs which you discussed. So that depends on luck. Okay, so one day, that is tomorrow, or if you ask for it Sunday, will be the programming part and the coding part, execution, that part, and Viva will be on some other day. Okay, so whenever they tell me, there will be a separate day allotted for examination. So then we'll be having Viva. Okay, so that will complete your lab course. Okay, so complete assignment 2, preferably by today. Okay, very simple assignment. Everything what we discuss in the class only will be asked. Okay, no conceptual questions, no nothing like assignment 1. Okay, you need not think too much into it. You should be completing in 5 minutes. Okay, straight questions. Okay, so let us see binary search tree. So till now we have been discussing about various data structures. We've seen arrays, we have seen linked lists. So each one has its own advantages. So say for example, we said array is very good at a random access. So any element you want to go to, directly you can go very fast. Time complexity is order of one, that is constant time operation. Linked list will take time. Okay, if the length of the list is n, in the worst case you may have to traverse the entire list. If the element you want to go is the last element, maybe, because the only way to go from one node to another is to the pointers. If you want to go to the last node, you have to go through all the previous n minus one nodes, no other option. So linked lists are very bad for linear traversal, searching for an element. Okay, but where linked list is very good is it is good for dynamic applications, because as and when you want a new node, you can create and just rewire the pointers. Arrays are very bad at this. Arrays are a fixed size. They cannot grow. They cannot shrink. If you want to add a new element, the only way is create a new array of a new size, higher size, copy all the previous elements, and add the new element. No other way. Okay. And even though we didn't have hash tables in our syllabus, that is one more data structure that is useful in some other applications. Okay. So various data structures are there. Okay. So all of them, if you see whether it's array or linked list, one of the disadvantages is searching. Okay. So linked list we saw it is n. Arrays are good at indexing, random access. If you know the index, you can go a particular index very fast. But if you want to search for a particular element, again it will take order of n time. Okay, there's a difference between indexing and searching. You tell me the index, array will straight away go to the index, no matter how you use the arrays. But if you tell you if you're asked to search for an element again, that will take time. Okay, so we are now aiming at data structures that will be efficient for searching data. Okay, so here we enter a new data structure called tree. Okay, we are not at started the binary search tree. That's a special type of tree. But before that, let us see what tree is. So tree will be something like, say for example, there will be no root node. Okay, and from the you can call it the parent node, and it having some child nodes. General tree is a general tree, so I'm not putting any restriction on number of child nodes. Any number of nodes. Say for example, the root node A here is having three children. Okay, B is having another three. So a tree is like this. One will be the root node, and then children will be coming from them. Okay, so that is the tree. Okay, so the last nodes which doesn't have the child nodes, we call them by a special name called leaf nodes. Okay, and at the same level, if two nodes are at the same level, for example, they have the same parent, these three B, C, D, we call them siblings. So there's some terminology in trees. Okay, then you can also define the depth of the tree and height of the tree. That will be more useful for your theory course, lab course. That's not important too much for us, but you can also define them. Okay, depth of the tree, height. Okay, and then let us start to put some restrictions. Okay, what are the restrictions? Now we start with a binary tree. Okay, still this is not binary search tree. Okay, we have seen a general tree. Now let us see what a binary tree is. So binary tree, a node can have, okay, no more than two children. So earlier you had a case where there were three children. For example, A has three children, right? B has three children. But now we are starting to put restrictions. Okay, a tree where any node can have no more than two children is called a binary tree. That is either 0 or 1 or 2. So this is a binary tree. Okay, so if you see any node, it has either 0 like E, 0 child, or just one child. Like for example, D has only one child, F has only one child, or it will have two child like A, two children. So this is a binary tree. Okay, so binary tree, every node will be having either 0 or 1 or 2 children. Okay, then you can also define what is a complete binary tree. The complete binary tree, as the name suggests, is completely filled. Okay, maybe except with the last level. Okay, but otherwise it will be more full. That is, it will be having two children at every level, except at the last level. Last level you can have leaf nodes. Right? Then we come to the binary search tree. So binary search tree, we now start to put even more restrictions to the binary tree. So binary search tree is also a binary tree. Okay, but in a binary tree there is no ordering. If you see, we're putting elements. All we are concerned is about the structure. You should have these many children and all, but we're never talking about the ordering. Now comes the order. In binary search tree, there'll be some properties that the node should follow. First of all, the left subtree will contain nodes, only those nodes which have lesser value than the parent node. Say for example here, for the node 8, to the left is a node called 3, and that value is less than 3, less than 8. Okay, 10 cannot come to the left here. Okay, 10 is greater than 8, it will go to the right. Okay, so that is one thing. The left subtree will contain only those nodes with keys less than the nodes key. So 8, if you see to the left, all these nodes are less than 8, and all these nodes to the right are greater than 8. That is one thing. Similarly to the right, left and right. Then the left and right subtrees themselves are the binary search trees. Okay, say for example, to the left of 8 is this is a subtree, and you can see this itself is a binary search tree. Say for example, if you now consider 3 as the root, and this definition is important because we'll be doing recursion. Okay, the way we code up binary search tree is using recursion. So this is very important. Okay, so that subtree itself is another binary search tree. It follows the property. So 3 to the left is 1 less than 3, and to the right are all elements greater than 3. Okay, and of course there should be no duplicate nodes. So this is the binary search tree. Okay, and what is the advantage is now we can search for elements very efficiently. If you recall the discussion we had on binary search algorithm, not binary search tree, the binary search, where we are searching for the position of an element. There we said in one single shot we can throw away half the elements. Okay, you recall binary search, the regular binary search, I think we discussed many times this. Say for example there are 100 elements, what we said, if the elements are sorted say from 1 to 100, if I'm looking for some element say 72, we go to the midpoint and ask the question whether 72 is greater or is it less than 50. Because it is greater, what we do, we can throw away this entire portion. We can be for sure that the required number 72 will not be towards the left half. Again we'll go to the new midpoint. This time it will be 75. Again you'll be asking the question, is the 72 greater or less than 75? Now because the element we are interested is towards the left of 75, we can throw away the right half. Okay, so every stage we are throwing away half. Similarly we are trying to achieve the same. If you see, what we're trying to achieve is like this. This makes searching very easy. Say for example you're searching for some element that is greater than the root node, then you need not go to the left node at all, this left subtree, because the element you are interested will be towards the right subtree. And if you correctly plan the tree to be, and that's why we had a definition called complete tree somewhere. Okay, we had a definition of complete. I think it must be somewhere. But what is a complete tree? The tree will be completely full, not like this. Okay, so here we are filling the F node before filling the E node. No, not like that. A complete tree is everything will be filled. So after G, this also will be filled. So every node will be having 2 children. So this will be having 2 children. If you plan your tree construction properly, this will be a very balanced setup. So there will be equal number of nodes, equal number of nodes. So half of the nodes can be thrown away if you're searching for one particular element. Okay, so what I'm saying is, instead of constructing the tree randomly, if you plan your tree properly, so every child, every node has 2 children. Okay, this you have to take care during the construction. If the tree is like this, then roughly half the elements are here and half the elements are here. Then if you're searching for some element, say the root node is 102 and you are searching for some element 257, then straight away we can traverse only this portion. We can straight away throw away the left half. Exactly what we have been doing in binary search algorithm. Provided you design your tree like this. If your tree is very haphazard, say for example it's like this, okay, it's very unbalanced, less elements here and more elements here. Okay, then in the worst case, say for example again it's 102, you're searching for 257. Here, even though you go to here to the right, you have to take care of so many nodes because you didn't construct your tree properly. Your elements more are towards the right subtree. Okay, so that you have to take care of. Okay, so this, are you able to see the linkage between binary search algorithm and binary search tree? The concept is almost similar. Okay, we want to only focus our search on one portion of the tree. Okay, and provided our tree is complete, almost complete at least, we can throw away one portion. Okay, either left or right. Okay, so that is binary search tree. Okay, so let us, for example, if a tree is like this, say 18, and this is some elements say 16, Here there may be a 24. It has two children, say this is 22 and this will be 27. Let us say this is 4 and this is 17. Okay, so like this. Say for example you want to search 27. So starting from here, you throw away this portion because 27 will definitely be towards the right subtree. And if you see, because this tree is having how many elements around, this is 4 6 7, around 7 elements. Okay, this tree is having only, this is having 3, this is 3, so equal number of elements. So you need to focus only half of the tree. Okay, provided the tree is what we call, the technical term is balanced. The tree is balanced, it is almost roughly the same elements on either side. You can take advantage and use the binary search algorithm which you'll be using. This is for efficient searching. Okay, so the reason why we are doing this is we want to search for an element efficiently. Okay, okay, fine. Desina is telling we'll discuss in the class. Okay, just let me know. Okay, so is this point about binary search tree clear? The reason why we are constructing the tree, the properties, why we are having those particular properties. Okay, is that concept clear? Why are we putting restriction on the binary search tree that the elements lesser than the root should go to the left and elements greater than the root should go to the right? What is the advantage? Are you able to understand why we are constructing the tree like that? Okay, can anyone tell me what is the advantage, why we are doing that? What is the advantage by putting this condition, these two conditions? What is the advantage? Can anyone tell me? Nodes having less value, then the root will go to the left and to the right will go to the right. Okay, traversal becomes easy. Yes, correct. Okay, for searching a particular element it will be very easy. Okay, is this point very clear, or you want me to repeat it? Okay, binary search, this is the key concept, the construction. If it is not clear, I will explain it again. So make sure that you understand this particular point. The reason why we are putting the particular restriction, elements less than the root should only go towards the left, elements greater than the root should go only to the right. Okay, is this point clear to everyone? Okay, fine. So then, so once we construct the tree, we have to do what is known as traversal. Okay, so traversal means visiting all the nodes. Visiting every node is called traversal. Now you can visit in many orders. Okay, there's no particular rule. If your goal is only to visit every node, obviously there'll be many options of visiting. Okay, so you have 3 traversal orders: in order, pre-order, and post-order. Okay, so traversal is nothing but visiting all the nodes. The reason why you want to visit all the nodes, maybe for example you just want to print out the elements in the list, in the tree, then you have to traverse. Okay, so how you traverse? So traverse can be having many methods. Okay, so say for example I'll visit this node first. I'm starting from the root node, and then maybe I will go towards this node, this left subtree, or you can go to the right. Okay, and once you go here, what to do? Whether you go left or right. Okay, so there are many options here. So traversal you can do in many ways. So which way you follow? So there are 3 popular ways: pre-order, in order, post-order. So that depends on the position of the root element. Okay, so there's a root element, there's a left element, and there's a right element. Okay, there's a root, left, and right. So depending on the position of the root, you can have, say for example, in order. In order means, as the name suggests, root will be here, L and R will be here. This is the left and right. So you first visit the left node, then the root, and then the right subtree. Okay, pre-order. Again, the names indicate the position of the root. Pre means before, so root will come first. Okay. Anyway, L and R will be in the same order, left and right. So see the root where it is. Here it is in between. Here it is. Here it is before, pre, and then as you might expect in post order, it will be towards the end. L and R will be first. So first you visit the left subtree, then visit the right subtree, and then have the root. Okay. So this is the 3 orders. Okay. So say for example, you have a tree like this, A, B, C, simple tree, three nodes. So in order, what we'll do, first of all, we'll visit the left. So in order will be B, then you come to the root and the right C. This will be in order. Pre-order will be, you first visit the root. So A will be printed first. You first visit that root node, then go to the left. and then C. Post order, straight away go to the left node, right node, and then the root element. Okay, so these are the three traversal methods. This is a simple tree, but then B itself can be having children. So then what you do after this, you have to repeat. So you'll be using recursion calling the same function. Okay, that we'll see how we code up. So those are the three traversal methods. Okay, so in order, visit all the nodes in the subtree, left subtree, then the root node, and then the right subtree. This is pre-order and this is post-order. Okay, so here is an example you can go through when you're having time. So this is in order. So in order, one easy trick to remember is in order will always give you ascending order. You see, because of the nature, what you're doing in order. See, you're visiting the left subtree first. So you go here, and you say, let me go to the left subtree. But after coming here again, you go to the left subtree. So what happens if you keep on going to the left? Because the property of the left binary search tree is elements less than the root node will be to the left. Okay, so obviously if you keep on going left, you will end up with the least element, and that's why in order you will print out elements in the ascending order. So this is one neat trick you can use. Okay, so in order will always give you elements in ascending order. Okay, so in order, then this is pre-order. So you see the root where it is coming, 38 pre-order. So you'll get the root first. In post-order, this 38 will be coming towards the end. Okay, so just practice. Since you're already doing this in your theory course, this should be easy. Okay, so if you're given a tree and I ask you to just print out the in order, I can ask anything in order, pre-order, post-order, you just should be able to do this. Okay, given any tree, binary search tree, if I ask you some traversal, you should be able to tell. That's a pretty standard question. In binary search trees, of course, you should be able to. There's a basic concept, traversal method. So be comfortable, practice a couple of trees. Okay. Then, if you come to how to code it up, okay. So as you might imagine, this heavily uses recursion. Okay, because I told you the left child of the root itself is a left subtree, is a binary search tree. Okay, so it is following all the properties. So again, you have to use recursion. Say for example, if you want to implement in order traversal, you know in order traversal is, first of all we visit the left subtree, but you see what we're doing here. Anyway, one condition you have to check, that is whether the tree is empty or not. If there are no elements in the tree, of course there is nothing to traverse. So that condition anyway you have to check. So the starting element, root element, will create a pointer and point to the root element. If it is null, it means the tree is empty, so there is nothing to traverse. So then you will come out of the loop, provided this root is not null. So now it means there are some elements, you have some elements to traverse, then you enter the loop. And the first thing in order is you have to go to the left subtree. Okay, but you cannot directly print that element. Okay, because again you have to call the function. So this is where the confusion might arise for some of you. Okay, you will be calling the function. This is a function called in order. Okay, so this is a function. The function is in order, but again inside the in order, again you'll be using the in order function. So this is recursion. The function will call itself. Okay, and the reason why we need to do is each child of the left subtree itself is again a binary search tree. Okay, so say for example, you have a tree like this. We are now doing in order traversal. I have given you access to the root element, and you know what is in order traversal. The root will be here and L and R. So first of all, you have to print the left node. So it's not sufficient if you print, let us say that how will the data structure will look like. So the data structure, say for example, individual nodes. Individual node, you have to create a data structure called struct. And what will each of these nodes contain? Of course, it will contain a data value, some value. Okay, so whatever this is, 12 or some value. And then you need two child nodes, because this is a binary search. So there will be left and right. And what are these? What will these be? They themselves are node. Okay, so for a node, the left and right child themselves are node. So what will this will also be node, but they'll be pointers. Okay, so be clear about this definition, how we define an individual node in a binary search tree. This you should be very comfortable. This we have been doing from the very first class, how a user defined data structure is created. This you have had questions in the assignment 1 also. By this time you should be very comfortable creating nodes in data structures. So this is a data structure we are creating called node. So each node in the binary search tree will be of this type. So what it will contain? It will contain a value and pointers to two other nodes, one the left child and one the right child. Okay, so this definition, be very comfortable. Okay, so now it is not sufficient, because in order says print the left element first and you have access to the root, you cannot straight away print, you cannot print root data. This you cannot do. The reason you cannot do is, say for example, this is 12, this is 6, this is 18, and this is say 5, and this is say 7. If you do this printf of root of data, what you'll get, you print 8 6. That is not correct, because again you have to, from here you have taken to go to the left. What is this saying? Print the leftmost element first, but after coming again you have to repeat the process again for this node. Now this is the new root, now this is the root element. Again you have to go to the left, again follow this process, left, root, right. Okay, so left, root, right. So that's why you have to use recursion here. Okay, so this will not be correct, you cannot print root of data. So that's why what you have to do, after coming here, you first of all have to call the function again. Keep calling the function, keep calling till you go to the leftmost element, then you print that particular data. Okay, so the order is, go to the left by recursion, print the data, and then in order of root of right. Now this takes time to sink in. Okay, this is a, even though it's just looking 3 lines of code, this is a very complicated code. Okay, the function is calling 2 times, you're calling. Okay, this is recursion. Okay, one time you're passing the left child, the pointer to the left child, and second time you're passing pointer to the right child. Okay, so and finally only then we'll be printing the data. So, okay, so the order, first of all, initially at the initial stages you can by heart this code, no problem. Okay, but over a period of time you should understand what this code is doing. Okay, it's very powerful, 3 lines of code. Okay, and just the order changes for, say for example, of pre-order. What we do in pre-order, first of all we'll print the root element, the root comes first, so you print the root element, then you call the pre-order function on the left and right. Post order, what you do, first of all call the root and left, root and right, then you print. Okay, so this is something that definitely will take time to understand. Okay, so in this simple 3 lines of code you can travel whatever huge, say for example the tree is containing 1 million elements, but you can print all of the elements using just 3 lines. That is recursion. This will keep on going, keep on calling itself till it reaches the 1 millionth element. It can do that. Okay, so recursion is happening here. Of course, what is getting passed, how it's getting modified will definitely take time for you to understand. Your first year students, okay, it will take time. Okay, but at least understand what the logic is. Coding part can come later. Okay, but initial stages, no problem, you can by heart the code, I don't mind it. Okay, but definitely you should at some stage understand what this code is also doing. Okay, so that is the code for the 3 traversal methods. Okay, so first of all, let us try to code it up. I have already posted the code for today. Okay, so in case anybody of you are working along with me, just open the online compiler and copy this code. Okay, so we are working with only one code today. So that code contains both creation. I think creation is not in your syllabus, only traversal is there. So we'll take a sample tree directly in the main function. We'll be not be asking user input. Directly in the main function, we'll create a sample tree and then just write code for the 3 traversal methods. Okay, so let us run. So I'm running the code for binary search tree. Okay, I think I have copied the wrong thing. This is the code. Okay, okay, let me see. I think I have given the wrong code. Just a minute. This is the code. Okay, I think I had to post it again. So please copy this code. It's the online compiler. Okay, so I'll just give a couple of minutes for you to open. Those who have access to computers or laptop can open the code. I'll just give you 1 or 2 minutes. Okay, so if I have opened this code, let me check whether I'm still connected. Okay, so let's see the code here. So your syllabus doesn't have any program on creation of the binary search tree. So it's only about traversals. So here we're already creating a tree. Okay, so we're not asking input from the user. Okay, directly we're creating a sample tree here. So this is the order in which you're inputting the elements. Okay, so if you see, there are two functions here. One is we're creating a node. This is creation a new node. This is how we create a new node. Okay, and then there's another function for inserting a node. So two helper functions we are taking, and then we are calling the function. First of all, let us see the traversal methods. This is what we have already seen. So what we do, for example, for in order, the parameter you have to pass is the root element. Okay, so this you have been already been seeing in many courses, in many programs. The starting element, say for example in a linked list, the starting element is represented by a pointer called head. That is the only access you have to the entire list. We will not be providing all the elements and passing as a parameter. Only one single pointer to the first element. In a linked list, that is head. In stack, we call it top. In queue, we call it front or rear. Okay, only some pointers will be available. Similarly, in tree, a tree might contain so many elements, but we will not be passing the entire tree. All the nodes you won't be passing. Only one single pointer called the root node. And from the root node, you can traverse the entire, that we already seen. From the root node, you can traverse the entire tree. Okay, so here in order traversal, all we need is the access to the first root element. So given that itself, how we are going to traverse the tree. So root, remember, is a pointer. It's a pointer to the first node. Okay, so I think this we already seen. So first of all, you have to traverse left. That is the order in which in order happens. Left, root, right. Okay, so first left. Okay, so this is recursion. This is the data you're printing, and then traverse right. Okay, so pre-order, the order is root, left, right. So root, okay, pre root. Okay, so print of whatever is the root, print the value, then left and right. Then post order, left, right, root. So left, right, and root. So that will be the traversal methods. So let us see how we create a basic node in this tree data structure. So we're providing some sample data, some nodes you're creating. So how to create one individual node. So this is the code how to create a node, and this you must be very comfortable. So this is just a malloc function. So this line of code is creating a data, a memory block of size, whatever the node size is, and returning a pointer. So we're storing it in a variable called temp. So temp is a pointer of type node. Okay, it points to a. Okay, so we are creating using a malloc function, asking the compiler to give us a memory block of size node. So it will create some space in memory. Say this is the node, this is the space occupied by one node data structure. So this block will give and give a pointer to the starting element. So this pointer will give. This we are calling it as temp. So this will return a pointer of type node. Okay, so temp is a pointer that points to a data structure of type node. Okay, so this is how we create. Okay, so because we want to create a new node, we are now building a tree. Okay, we are now building a tree. So we're asking, give me a node. We want like this. The tree will be like this. Okay, the pointer allocation will come later. This arrows will come later. But first of all, you should be able to create a single node, and this is how we create a node. Okay, so this line will give you the pointer to the first node, and then you populate it with the value. So here you're asking in the function from the user. You say for example here some function in the insert function. I think you're calling somewhere new node of key. Okay, so then this function gets called, and this parameter, whatever is the value you want to enter, will be passed as parameter. Okay, so this will be the value for this particular node. Okay, so this arrow notation, temp of key means that this value will be populated here with whatever value pass. Okay, so that will be, these two lines of code will now create a new node and fill its value with whatever that item value is. And then because this is a basic node, single node, we will create the left pointer, the right pointer, and point to null because this is a single node. Okay, and we return that pointer temp. Okay, so what we're doing in temp, So the create function, okay, first of all, it's creating just a basic node with no children. This is null. Okay, we will use this basic node to build the tree later. Okay, but the basic first step is to create a one single node, and for this node right now there will not be any children. So if some function is asking to give me a single node, this is what you do. What you give? You give a pointer. Okay, you create this node and you create access, say for example temp, and return this temp to whoever is calling. Okay, so the function insert function will be asking to create a node. Then you will be using this procedure. Create a node, just make the left and right children null. Okay, and provide access to it in the form of a temp variable, and this is the pointer, and pass this pointer back to the calling function whoever asks. Okay, so that is what this line of code is doing. Okay, so create memory block, populate with the value, make the left and right children both null, and return that pointer. Okay, and that's why the function signature is like this. What is the return type? It's a pointer of type node. This temp is a pointer of type node. So this is what the creation is doing. This is a function to create a new node. And how will you be using it? Say for example, you are now building a tree. The first is the root node is 38. You want to insert 38. So right now the root is null. This is a blank tree, so root is null. So now we want to insert the first element, that is 38. So now obviously we have to create a new node. So first of all, we were writing a function called insert. So here is the insert function. Okay, and in the insert function we will be making use of this creation new node. Okay, we'll be calling the new node function here. Let us see how we do it. So the insert function will take these two parameters. So what are these parameters? One is with what value you want to insert. So this will be the, here we are taking integer data type. So we're asking what is the value you want to insert into this particular node. Okay, so here we are saying I want 38 value to be inserted. Okay, so that is one of the parameters. So insert function will take the value to be inserted, and will take also what is this parameter, what do you want to give to the insert function. So you should be giving the parent node. So, okay, let's just say for example this is already a tree like this. Okay, say for example this is a tree. Now we are having an insert function. So what should this function parameters be? First of all, anyway, of course, say for example the value, if 25 want to insert. What else you want to tell? You should also tell what should be the parent node. Okay, where you should insert this. Okay, so actually if you see 25 will come somewhere here, because it's greater than 12, is greater than 18. So the correct place for 25 will be in a binary search to be here. Okay, so the parent should be this. You have to pass this. Okay, so insert function is asking what is the parent to which you want to attach this new node. Okay, new node you can create using the new node function. But what will new node give you? We just give you a node with the left and right children as null. You have to insert this somewhere. Okay, so the insert function will take it and insert this new node. This will call the new node function, get back this new node, and insert it at the correct place. What is the correct place for this particular node? It is here. It should be the right child of 18. Okay, so what the insert function is doing, it is finding the right place. It is not inserting as an arbitrarily, randomly, it's not inserting. Okay, the insert function is finding the right place for this node. Okay, based on the values, it knows what is the value of the root. Okay, so 25 is greater than 12, it will go here. Again, it will make the check, it will go here till it, when it will go till it finds there is a null element. So initially this element is not there. So 18 to the right is nothing, is null. So then it will realize this is the right spot. It will insert 25 here. Okay, so this is how insert function works. That's exactly what this code is doing. Okay, first of all, it is checking whether that is the empty tree. If it's an empty tree, there is nothing to do. That's the single node you can insert. Otherwise, if there are already some nodes, what you do? You first find out whether the value you want to insert is less than the root element. Then you have to go to the left. Okay. Otherwise, you have to go to the right. And again, here is recursion. You just don't want to insert at the immediate right child. If the right child itself is the right subtree, again you have to traverse. Again, recursion here. Complex piece of code. Okay, this binary search tree code will be uh, conceptually it's very easy, but when it comes to coding, you have to be very careful. Okay, because you'll be calling recursion. Okay, so you're in the insert function again. You're making use of insert. Okay, so let us once again try to see this. What we're doing. Say for example, there is a tree like this. So there's a 15 here. There is a say 7. There's a 20 here. This has two children. Say 6 and 9. Let's say this is 15. After 15, it should be like say should be greater than 15, right? Okay, say 16. It's a 20. It should be say 22. So there's already an element here. Say this is 21. Okay, so say this is the tree. Now I want to insert 27 into this node. Okay, so what should my first step be? So straight away, so the only access to the tree I have is the root element. Okay, so first of all, I'll make the check whether the root, the value is greater than or less than. So obviously this 27 is greater than 15. So this has to go towards the right. So you cannot make the simple check. You cannot say 27 is greater than 15. So straight away, make this 27 as the right child of 15. You cannot do that. You cannot do that because there's already a node here. Okay, if there is no node, you can directly attach. So there are two conditions here. Okay, so whether it is null or not null. Okay, if it is null, you can directly attach this 27 node here. But you can see here that 50 is already having a child. So again, you call recursion. So now this will be the new root, and now you check whether 27 is greater than 20 or not. 27 is greater than 20. So again, go to the right, but again, use recursion to create again asking the same function insert. Again, we're asking, is 27 greater than 22? Yes, is it greater than 22? And this time there is no node here. This is right now null. So now you can insert. Till the point you find null, you have to keep doing this process. Okay, now you find the null node, you can directly insert 27. This is the right position for 27. Okay, so that is how insertion works. You have to keep calling that function again and again. This is just a single step. Don't do this. Don't compare with the root saying is 27 is greater than 15. Put it here. It cannot go here because there is already another node here. You have to keep repeating the process. Use recursion. Keep on going till you find the correct spot for that node 27. And that will, when will that happen? When the parent node has a vacant spot, that is null. Till that point you have to be traversing the list. Okay, so that is this is the code here. Okay, so if you see now, let us try to see the code once again. What is the insert function doing? Is first of all comparing whether the value you want to insert is less than the root node. If it is less, what you're doing, you're again calling the insert function, now making the new root. What is the new root? The new root now is node of left. Okay, this is recursion. Okay, similarly, if the value is greater, for example, the value you want to insert is greater than the root node, then you have to go to the right. Okay, so this is how insert function works. Definitely complex piece of code. It will take time for the concept to sink in here. It will definitely take time. Powerful, very powerful line of code. Okay, insertion in binary search tree, you have to trace it line by line what's happening. Okay, so at least, okay, if you're not very comfortable with the code part, at least you got an idea, at least like 50% what we're doing, the direction which we are doing. Okay, the approach we are taking, if you're understanding, that is sufficient. Okay, you have to practice this. You have to take an example and construct the binary search tree from scratch. You have to construct the tree, not using compiler. Okay, by hand using pen and paper, you have to build a tree. Okay, then you'll understand. Okay, but at least the concept is the concept clear, how we are creating a new node and how we are inserting. Okay, at least the theory portion is clear. Coding part can take time, no problem. But is the theory portion clear? Or is it totally confusing? Why no responses? Totally confused. Okay. Okay, so in the handout, so I have the sample example which I've taken. Okay, this exact example which I've taken. Okay, this 38 545. Okay, so this example, whatever we taken in the code in the handout, I have traced each and every step. Okay, so there'll be total. So how the tree is getting built? Starting initially is a null node, the tree is empty. What happens? How the tree is getting built? You see the tree slowly one node is getting added, and by the time you complete the code, the tree will look like this. Okay, so there are 32 steps here. Okay, so when you have time, you go through this code. Okay, this I'm not explaining in the class. It will take time, too much time. But when you're free, you check. Okay, if you can understand all these 32 steps, what is happening, then you will have a very thorough grip on how recursion is being used in this particular example. Okay, because it's changing. Okay, so one time the root of the tree will be the root, but when you call recursion, the left or right side will be the new root node. Okay, and then again you have to call recursion. So what is happening behind the scenes is what this particular table will give you, how the tree is getting built, how each node is getting added, and what is the corresponding code. Okay, so when you have time, you go through this. Okay, so all this number of steps, 32 times this is being called, but you're not seeing all of this in the code. Code is so compact, and that is the beauty of recursion. You'll not find that complexity in the code. The code will be very simple, but behind the scenes, so much will be happening because the function calls itself again and again. Okay, recursion definitely takes time to understand. Okay, it's not an easy topic. Okay, you have to do many examples. At least for starting, you go through this particular table and see how the nodes are getting added and how finally we end up with this tree. From a blank tree, how you came to this, what are the steps involved is mentioned in this table. Okay, so when you have time, go through. Okay, so that will be binary search tree. Then before we conclude on binary search tree, so as I already told you, when constructing the tree, you should be very careful. Okay, say for example, elements are entering in some, say for example, there's an element here. Okay, it's coming like this. Some elements are coming randomly, and now you want to build a binary search tree. Say for example, 14 is first element, that will be the root. 28 will end up here, 6 will go here, and 7 will be here. 25 will be here. 35 greater here. 35. 47 will be here. 2 will be here. 8 and 9. So this will be 8, and this will be 9. Okay, tree will be like this. If you see on a random basis, if really things are random, you'll end up with almost a balanced tree. Like there'll be almost same number of elements to the left or right. Let's say for example, you are very unlucky and things, say for example, the elements are entering like this. Say for example, like they're entering in some sorted order. You're just unlucky that the elements are entering in sorted order. Now you want to build a tree. So 2 will come here. Where will 14 go? So greater it will go here. 27 will go here. Okay, you see what's happening? The left tree is not at all getting populated. Okay, this is entirely empty. It's just that elements are coming in a particular order. What is this actually? Is not even a tree. This is just a linked list. Okay, you have ended up with a linked list instead of a tree. Okay, and this is exactly what we didn't want. The reason why we started with trees is traversing a linked list is difficult. Okay, say for example, I want to search for an element 89. This is exactly a linked list. Again, I have to do it in order of n. I have to search the entire list from here to go here. So this is a bad case. Okay, we are unlucky that the elements are ordered. Okay, so there will be occasions where, depending on the order in which your data comes in, you might not get a tree which you like. You might end up in a very worst case having to search in order and complexity. But this is what we don't want. We want log and complexity. A binary search algorithm, that's why it works well is if the data is already ordered, it will be log and complexity. Here, trees is different. The data is coming in a sorted order. It's not helping you. Okay, so then what we do, it's our duty to make the tree balanced. Okay, so there is a separate session that we don't have in our lab syllabus. Okay, so there are separate trees which make the tree balanced. Okay, so there are many trees. Okay, so say for example, there's an AVL tree, there's something called a split tree. Okay, there are red black trees. Red black trees I think must be in your syllabus, but these we don't have in our lab syllabus. But the theory part, at least this point, you remember. Okay, if data comes randomly, there's a good probability that roughly half the elements will end on the left subtree and right subtree, then it's okay. But sometimes you'll be unlucky if the data comes in sorted order, you'll be ending up in a linked list sort of fashion, and then all the advantages which you wanted in a tree, there is log n time for searching, that will not work. You'll end up with a order of n complexity searching. So then what you do, you will try to make the tree balanced. And how to balance the tree, that is not required for you. It's not in the syllabus, but we have AVL tree and split trees, most commonly used. Okay. And anyway, I think AVL trees are not that popular these days. Mostly are using split trees only. Okay, at least remember the names and the concept of balance. What do you mean by a balanced search tree? So theoretically, the definition is if the height of the left tree and the right subtree differ by not more than one, we call it a balanced tree. Okay, they need not be exactly same. Okay, even if it is, say for example, this is a tree, this is a balanced tree. Okay, the height here is, this is the height and this is the height. Left subtree, say for example, you have 3, this is 4, it's okay. They're differing maximum by 1. This is 4 and this is 3. That difference we can accept. Okay, but you can't have a, okay, this tree is going too fast. Okay, you can't have this setup. Okay, so this is a balanced tree. So balanced tree is a tree where the height of the left and right subtree differ by not more than 1. In that case, we call it a balanced tree. And it's always it's our target to make the tree balanced so that we can search efficiently. Okay, a perfectly balanced tree will take log n comparisons to find the element. Okay, so just keep that point in mind. Okay, we cannot insert as in how we get the elements. We have to keep the tree balanced. So how we keep the tree balanced, at every stage when we get an element, we will ensure that the tree is balanced. Okay, say for example here after 1 and 2 we get 3. We will not keep 3 here because that is making the tree balanced. The height of the left subtree is 0. Say for example, elements are coming in this order 1, 2, 3. Okay, so 1 you have put here, 2 you have put here, now 3 is coming and now you are concerned. Okay, so the tree is really becoming unbalanced because now if you put 3 here, okay, there are 2, this is the height and this is no 0. This height is 0 and this is 3. This is not making a good case, so you will not put 3 here. Okay, so what you do, you'll try to rebalance the tree, but you cannot keep 3 here. Okay, that will defeat the purpose of the binary search tree. The property is not maintained. 3 is greater than 1, so it cannot go here. Not make 2 the new root. Okay, how about this? We can rearrange the tree. Instead of before putting 3, just make 2 the new root and push 1 here. So now this is a binary tree. 2 is the root element. Elements left less than 2 are to the left, elements greater than 2 are to the right. Okay, so earlier, if blindly, dumbly you inserted, you end up like this. But now you're ending up with a perfectly balanced tree. Okay, this is what you do. At every stage, when you're getting elements, you insert the element if there is no problem. Now we can insert 4. Okay, the height is not very much disturbed. The height is different just by 1, the left and right side. Okay, so if it really falls out of balance, then you rearrange the nodes and try to make the tree balanced. Okay, so that is very important in practical applications. Okay, otherwise you will end up with a very bad case where you might end up with a linked list. You have to do all the order and traversal. Okay, so that is one point. Even though we don't have code for AVL trees and split trees, this you have to remember the reason why we do this. Okay, so that might be a question in Viva. Okay, the reason why we keep the need to keep trees balanced. Okay, so uh, is that point clear? Why we are trying to balance the trees? What is the need to keep trees balanced? Okay, not clear? Okay, Desina says it's okay. Okay, so that is the last point for binary search tree. Okay, so with that we complete the coding part, whatever is there in the lab syllabus. So now comes sorting. There are 3 programs in your lab syllabus: merge sort, quick sort, and heap sort. But as I told you, we will not be taking up the coding portion. That is not required. Okay, I'm assuming we're working with the 70% syllabus, but I will cover Just to make the syllabus complete, I'll just go through, just tell you what the sorting methods are. Because sorting is a very important topic in data structures. Anyway, you have to know about it. Okay, just because it's not there in the syllabus, that is not an excuse to skip it. Okay, because data structures will be following everywhere. It's important for your after you if you write any competitive exams is important. You go to any company interviews is important. Okay, so data structures will not leave you. Okay, so better to have a idea on all the topics. So even though we'll not be doing the programs on sorting, I will tell you the three sorting methods will be just a brief overview. Okay, so it's 12 o'clock. I think you can take a 5 minutes break. And after coming back, we will taking sorting. Only the theory portion. Okay, will not be taking coding. Okay, 5 minutes break. I think I didn't run the code. Okay, did I run the code? It's very simple. Okay, there's nothing to do. There's no user input directly. It'll ask you the option to say, for example, in order. I told you in order will give you the elements in sorted order. I can see the elements are in sorted order. Okay, so code is very simple to execute. I think it didn't show the execution, but there is no need to ask the user input because we are constructing the tree here itself in the program. So the output will just ask the one or two or three, which in order which traversal method you want, and the output will be coming. Okay, so we can take a 5 minutes break, and after that we'll be starting sorting. Okay. Okay, so we'll restart the session. So we'll start with sorting today. Okay, so this is not for your lab syllabus. No programs will be asked in your exam. This is only for a completion of the, just to give an idea of the sorting techniques we use. Okay, we already done one sorting when we discussed about binary search algorithm. I told you that the prerequisite for binary search is the list should be in sorted order. So there we already applied a sorting algorithm called bubble sort. But if you recall, I told you that the time complexity of bubble sort is n square. N square is not a good sorting algorithm. Okay, n square is very bad. Okay, I think this is a question I already asked you now. The internal assignment one also. Yes, I think I gave the example where, say for example, the list is containing 1,000 elements and it's taking 5 seconds. Okay, to search. And now I'm saying the size of the elements is increased to 3 times. Now I'm asking what is the new time. Okay, and the complexity is n square. Okay, so n square means is making it 45 seconds. Okay, making the size 3 times, increasing the list of the size of the list 3 times is making time 9 times. So that is why n square complexity is very bad. Okay, so now we are trying to sort the list using some efficient algorithms which can do it in. So the new complexity we are looking at is n log n. Okay, so this is the best case. So all of your commercial, say for example, you have Java, okay, you have Python, all these programming languages will have inbuilt sorting functions. So when you use programming languages, you need not write your own sort functions. So the sort function will be available. So these languages will be having inbuilt sort function, which you can just call it. Okay, you can pass the elements, the list array element, and it gets sorted. You need not write your own sorting program. So internally, the, the, the sorting programs they use is the programs which you're going to discuss right now. Okay, so there are three main sorting algorithms, and all of them do the job in n log n sorting time. Okay, so n square we never use. None of the programming languages inbuilt functions use bubble sort. Bubble sort is just for introducing you to the concept of sorting. But in applications, we never use n square. Okay, this n square is a very bad sorting time. Okay, so n log n is what we will be aiming at. Now there are some sorting algorithms that can also do the job much better in order of n, but that requires the input to be in some special. The conditions will be imposed. Okay, so there are other sorting techniques which you might encounter in coming courses. Say for example, there is a bucket sort, count sort. Okay, there is a topological sort, all sort of sorting algorithms depending on the particular use case. Okay, depending on whether the input is satisfying some conditions, you can also get order of n complexity. But this is not a general case. If you're looking at a general purpose sorting algorithm, right now the best sorting algorithm which is used, quicksort, is mostly used. Okay, most of the programming languages use quicksort as the internally as the sorting algorithm, but others are also good. Both merge and heap also will give you n log n complexity. So this is the time complexity we are now trying to reach, which we are unable to get in bubble sort. Okay, so let us see what sorting is. As you know, sorting means you have to just sort the elements in a particular order, and in a business setting, you can just imagine the need for this. Okay, so companies operate on millions of products. Okay, and if you type something, if they want to give the result back to you, if the list is unsorted, there is only one way they can get the element you are interested in. Say for example, Amazon has so many millions of products, and you, for example, wanted to buy some Dell laptop or some model, and how is Amazon going to search in so many millions of products if the list is not sorted? Okay, if things are sorted, say for example, there is a shirt here, okay, there's a laptop here, okay, there is some other product. If things are not sorted, and this is running into some millions of products, the only way it can search is item by item it has search. Okay, so in business applications you can clearly see what is the need for sorting. They have to keep things in sorted order because they can retrieve. Ultimately you have to bring, the customer will be asking some data. All your search engines, for example, like Google, work on retrieval. This is information retrieval. Okay, the data is already stored somewhere, and you now want to get a particular set of the data satisfying a condition. Okay, then if your list is not sorted, you will be taking forever to get the item. So first of all, you have, you have to keep the list in sorted order. Okay, so that is the requirement. Okay, then let us see. So all of these algorithms use what is known as the divide and conquer paradigm. So this is one of the approaches we use in computer science, not just in data structures, but you will see this particular concept coming in many other courses. So divide and conquer is, uh, I'll be showing you in bird sort what we do. Okay, so first of all, merge sort and quick sort also, both of them use the same divide and conquer approach. So what it is, we'll see. So say for example, I have say 8 students answer scripts. Okay, so these are students having these roll numbers. Okay, so I have 8 answer scripts and I want to place them in a sorted order. That means in this order. Okay, I want to have the students answer script roll number 17 first and then 27 in sorted order. Okay, so how I'm going to do this is I will split it into 4. So the first 4 elements, okay, I'll give to one student. So I'll pick 2 students. Okay, I'll just delegate the responsibility. I will not do it. I will just pick 2 students, and give the first 4 papers to the first student, and the second 4 papers, the last 4, to the other student. And what I tell them, I just tell them sort your papers. So the first person will be sorting this list. So what he will be getting, he will be getting this order. Similarly, B will sort his own set of 4 papers and give me this order. Okay, so say for example, I now have, say for example, some 8 numbers. Okay, and these are not in any particular sorted order. Okay, okay, now I want to sort it. So what I do, I take half of them and give to one person, and I ask him to give me it back in a sorted order. So what this person will be giving is, okay, this is already in sorted order. Say for example, this is 17, this is 11. So this person will be giving me this after sorting. Okay, and this person should give me like this. Okay, so this is the requirement. Okay, whatever I have, I just split it into 2 halves, and this person will give it in sorted order. So what will I do? So this person will give me back this list, this person will give me back this list. So now can I just put it together and say this is the final sorted list? Can I just club these two like this? Okay, and can I say this is the final sorted order? Will it work that way? Okay, can anyone tell me? After the persons A and B give me back their own sorted lists, if I just club them together, will I end up with a sorted list? No. Yes, clearly answer is no. Okay, because this list by itself might be sorted. By itself, this 4 might be sorted. But when you put those 4 together, they will not be sorted. There is no compulsion. Clearly, you can see here, 6 should be the first element, but that's not happening. So after I get back the sorted list, there is some work that I have to do. Okay, so what is the work I have to do? Say for example, I have, this person has given me a stack of papers with 11 on top. Okay, this is a sorted list. The other person has given me like this. Okay, so this is what I will do. Okay, I'll start it again. Okay, so this person has given me his own set of papers in some sorted order. Okay, so the second person has also given me his own list, say 19 and 32. Okay, so now what I do, I will compare only the top 2 elements. Okay, so remember these lists are already sorted. So one thing I can be sure is the least element will be either here or here, because these themselves are sorted lists. So in this list, the least element is here. In this list, the least element is here. So the least element of the entire list obviously has to be either these two lists. So all that I do is I'll compare the top 2 elements. 6 is the least element. I will declare that is the least element in the entire list. And now the 6 will be gone. Now the list is only 12, 19, and 32. I again do the same. Okay, again compare 11 and 12, because now in the new list, 11 is the least in this list, 12 is the least in this list. The least element of the entire 7 elements, the remaining 7 elements, should be either 11 or 12. Okay, now because 11 is the least, I put it 11. Now 11 will be gone. Now the new list is 17, 25, 36. Okay, 12, 19, 32. Again do the same. Okay, compare just the top elements. So now 12 will come here, this will go. Okay, then I compare 17 and 19, 17 will come here, now this will go. Now compare 25 and 19, 19 is here, 19 goes away. compare 25, 32, 25. You see the list is getting sorted, okay? Okay, this is how we sort using merge sort. Okay, first of all, split it into two halves. Ask those persons to give back the sorted lists, and then when you get the two sorted halves, you do this procedure. Okay, and then you end up with the final list. And as you can imagine, what's going to happen? A very large list. Say, for example, I have 1 million elements. So I give 5 lakhs here, 5 lakhs here. You can assume these two persons, A and B, will do the same. They will again split it into two halves. Okay, give them to two other persons. They will give back the sorted list, and the procedure which we did just discuss, A will be applied, and A will get the sorted list like this. This goes on. Okay, we are using recursion. Okay, so that is how merge sort works. There are two steps in merge sort. One, we divide it into two halves. Okay, give one half to one person, give the other half to one person, and then the second is after getting back the sorted list from the two persons, you have to compare the top two elements and merge them. Okay, so that is what merge sort is. Okay, is merge sort clear? Just the procedure. We will not be going into the coding portion. What merge sort is doing, how we are sorting the two lists, is the concept of merge sort clear? Dividing into two halves and then merging it back. Okay. Pujita says yes. How about others? Okay, Dheeraj says yes. Okay, so that is merge sort. So let us see one example here. Okay, say for example, this is the list. This is a unsorted list. Okay, 84, 27, 49, and this is an unsorted list. What I do, we split it. The first four elements go here. The second four elements go here, and again A will be splitting it into two parts. So the first two 84, 27 go here. So everyone will be splitting till the point we reach single elements. Okay, so G, the person G has ultimately got only single element. Once you get a single element, there's nothing to do. What do you do to sort a single element? It's already sorted. We call it is trivially sorted. That is what we say. Technically, the term we use it when we have only one single element is already sorted. It's trivially sorted. So now G and H will be giving back without doing anything. They'll just give back the element 8427 to C. And then we know what C should do. C should compare these two elements and put them in order. That we already seen. Okay. So that is how. So this example I have just elaborated. You can go through. It's just explaining what I have just told you. Okay. You can go through. Okay. So that is merge sort. And once we get back the merge list, say for example, the first person has given back 12, 44, 58, 62. This is a sorted list. And the second person has given back 29, 31, 74, 80. This is the second sorted list. I told you how we are going to merge it. We compare the top two elements. Compare 12 and 29. So 12 is the least element. So that will be the least element in the entire list. Now 12 gets grayed out. Okay, this is no more in the list. Now 44 is the topmost element. Now compare the topmost element 44 with the topmost element of the second list. So now 29 is the least element. So 29 will be the second least element. Now 29 is gone, it's grayed out. Now 31 comes to the top of the bundle. Now compare 31, 44. Now 31 like that. Okay, so this is how finally you end up with the sorted list. Okay, so two phases. One is the divide phase and another the merge phase. Divide phase is just divide into half recursively. Okay, the first person will split it into two halves, and this person again will be splitting. So recursively will be splitting it into halves. That is the divide phase. And then in the merge phase, I told you what to do. Okay, when we get back the sorted lists, you have to create a new list, and this is how we merge the two sorted lists, and finally end up with the sorted list. So this is merge sort, and there is some code that is not required for us. Okay, so we'll not be taking up coding again. So that is merge sort. Okay, and the complexity is n log n. Okay, why it is n log n? Is it is n log n because, say for example, the total. So at every stage we are dividing into two. So you can clearly see what's happening. So what will be the depth of the thing? So say for example here there 100. Say for example, say 2 power 4 elements. Here you're splitting into two halves. So this is 2 power 3, 2 power 3, half. Now again you're splitting 2 power 2 elements. This again gets split 2 power 1. Okay, at every stage you're splitting into half. So what happens finally? 2 power 0, that is single element. Okay, so how many levels? We got 4 levels. What is that 4? That is nothing but log n. That is the number of elements. Number of elements is 2 power 4 to the base 2 is 4. So the depth, this height is log n. Okay, the maximum levels you get is log n. And at each level, what is the work you're doing? Okay, at each level you're doing, the work is n. That's why it's n log n. Okay, at each level you're doing, say for example here at this level, you have n by 2 elements. Say for example this is n. At this level you're getting n by 2 elements, n by 2 elements. And what is the number of work? What is the amount of work? You have to do just comparison in the second phase. So take the n by 2 elements, n by 2 elements, compare them. So how many comparisons you will do? The maximum will be n. Okay. So totally n log n is the time complexity for merge sort. Okay. So any doubts regarding merge sort? Okay. Is the concept clear? Merge sort. Only two steps. One is the divide phase and other is the merge phase. Okay, so can we go to the next sorting, quick sort? Any doubts on merge sort so far? Efficient algorithm. Merge sort is very efficient. Only problem with the merge sort is space complexity. If you see what we're doing after getting back the sorted lists, you have to create a separate list to capture the sorted elements. Okay, the space complexity here compared to other, you will see in the coming sorting, that is quick sort. Quick sort will be moving the elements here itself. So in the given list itself, in the given array itself, you can move the elements here and there, and you will not need any additional auxiliary space to get the sorted list. Okay, quick sort does what we call as in place sorting. In place means within the array itself, it will move the elements and provide the final sorted array. Merge sort is different. Here it cannot do like that. Okay, merge sort will take up additional space, and here you'll fill the answer. Okay, so while all of them will have the same time complexity, space complexity wise, merge sort is at a disadvantage compared to quick sort. Okay, that we'll see shortly why quick sort will not have that problem. But it's merge sort concept clear to all of you? Okay, then if it is clear, let us move the next algorithm, that is quick sort. Okay, so what we do in quick sort is we select an element called a pivot element. Okay, so that could be any element, arbitrary. But as you go deep into the subject, you will find out that there are some elements that are more suited for pivot. But in initial stage, you can consider any element, no problem. So pick one element, and what we do, you just, so there are some elements here. Okay, it could be 5, it could be 12, 2, 6, 16, 34, 11, whatever you want. You pick any element. Say for example, this is the pivot element. I'm considering the pivot element. I will take the pivot element, and all elements less than pivot, I will dump this side. So what are all the elements less than 11? This could be 5, 2, 6, again a 2. Because all elements less than the pivot, throw on one side. All elements greater than pivot, throw it on the other side. And recursively do the same. Okay, for now for this, take any pivot element. Say again the last element. Now all elements less than or equal to, put it this side. All elements greater than the pivot, throw on the other side. Here also. Okay, for this half, if this is the pivot, all elements less than the pivot goes this side, and all elements greater, okay, all are here only. There is none here. Okay, keep doing recursively. Again, two elements are here recursively. All elements less than 6 go here, nothing here. This is the end. Okay, now here we have only 11, 12, 16. Okay, so all pivot is 16, say for example, less than. So actually in the array itself, you're moving here and there. Okay, you're not creating any new space. And finally, if you see, you're getting the sorted. You traverse the leaf nodes, you will see the list is sorted. 2, 5, there's a 6, 11, 12. Okay, so the list is already sorted. So that is how quicksort will doing. Okay, so once again, we'll take a pivot element, all elements less than pivot, throw on one side, all elements greater than pivot, throw on the other side, and do it recursively. For the left portion, again do the same thing, selecting a pivot element. For the right half, again do the same thing. Okay, and then you'll end up with sorted list. Again, you'll be using recursion. Time complexity is again same n log n. The only problem is in the worst case, it will be n square. Okay, merge sort, best case, worst case, everything is n log n. Quick sort, it will be n square, the worst case. Okay, so is the concept of quick sort clear? What we're doing? The arbitrary may select the pivot element. Any element will do. Okay. So what we're doing in quick sort, is it clear? Just understood why we are doing, or do you want me to repeat it again? Quick sort. So you can see the example here. I'll show you an example here. So this is an unsorted array. So here I'm taking 50 as the pivot element, the last element is the pivot. So all elements less than 50. So these are all the elements less than 50 will be coming here. Okay. So from this left, what are the elements less than 50? In this list will be 24, 45, 12, and 31. All elements greater than 50 will be coming to the right side. Now do it recursively. For this left subarray, again you do the same thing. Say for example, the end element again is the pivot. Okay, all elements less than 31 will be going here, 24 and 12. All elements greater than 31 here. Similarly, 96 is the pivot. The last element we are taking as a pivot. All elements less than 96. All the elements are here. No elements are more than 96. That's okay. So this is how we continue, and ultimately we end up with this list. Okay, so the end nodes, the leaf nodes, you just go on, you'll find that is the sorted list. Okay, so 12, 24, 31, 45, 50, 63, 85, 96 is the sorted array. Okay, is the concept clear what we're doing? How we do it programmatically is a different aspect, but what is quicksort doing? How we are getting the sorted list from the unsorted list? Is the procedure clear? Quicksort. Nobody has understood. Okay. Okay, so Nitya and Gyaneswari says they have understood. Okay. So the time complexity is an n log n, but in the worst case it would be n square. And the worst case will be like, say for example, you select a very bad pivot. Okay, so say for example, the list is already in a sorted order. Okay, so list is already in a sorted order, and you chose a bad pivot. In this case, you selected the last element. So what we do, this is the pivot element, all elements to the left. So all elements will be coming here itself. No elements here. There is no divide and conquer. You cannot make use of divide and conquer. Okay. So again, here, take for example, this is the last element. All elements less than 67. Everything will be ending up in the left subarray. No work to do in the right subarray. Okay. So if the list is already sorted, then it's a bad case, bad input for quicksort, and the time complexity will be n square. Okay. But still, quicksort is the most popularly used algorithm because this sort of input you rarely get. Okay. We will be discussing the best case, worst case, average case, but worst case is not something. I mean, we are preparing for the worst case, but real life we do not get these cases. Okay, unless you're extremely unlucky. So we will be using quicksort in most of the practical applications, even though the worst case complexity is n square. These sort of inputs do come very rarely, so we go for quicksort. Okay, even though the worst case is n square, most of the time you will get n log n complexity. Okay, so that is quicksort. There is also small coding here. That's not required. Okay, then there is a heap sort. Okay, so heap sort, there is a linkage with heap sort and the trees. Okay, so heap is also a tree. Okay, so heap is it's a complete binary tree that satisfies the heap property. And what is the heap property? When we say heap property means, say for example, it's a max heap. Two types of heaps: max heap and a min heap. Max heap means the topmost element, the highest element will be at the root. Okay, so this is a max heap because the highest element is at the top, and this is a min heap. The least element in the entire tree is at the root, and this will be useful in, say for example, implementation of priority queues. Again, things like that will be useful. So this of all three algorithms, heap sort is actually a bit complex. Okay, so you have to call a heapify procedure. You have to rearrange the nodes, even though it's not required for you. But if you have time, you can go through. So merge sort, quick sort, and heap sort are the three most popular sorting algorithms widely used. Okay, and time complexity again is analog n. Okay, so even though sorting is not uh, in the lab syllabus which we will be covering, we will not be taking up any programs. I thought just giving you a basic introduction to these important concepts. These are very important. Okay, even if you're preparing for competitive exams, very important. Sorting the topic of sorting is very important. Even if you go for interviews, very important. So don't skip it just because it's not there in your 70% syllabus. Even though it's not there, some time later, if you have time, even if you go to the subsequent semesters, take time to go through those important concepts. Okay. So, but for an exam, for a lab exam, these three programs are not required. Okay. So that is as far as sorting is concerned. Trees. The topic for today, most important, is binary search tree and traversals. So if you are comfortable with that, that is sufficient. So any doubts on sorting so far? Actually, with this, we have completed all the lab programs. So what about the records? Are you writing the records? Has anybody completed observational record or yet to start? Okay. So will it be completed by Monday? Because if they ask you to submit the records online, okay. If they ask you to submit by Monday, can you do it? Okay, okay. Because I have to check up with the schedule. I'm not really sure when are they asking to conduct the exam. We need more time. That is not in my hand, Jagadish, because there'll be a date announced by the first year coordinator. No, I can't give time. Okay, it's not for me. Okay, so they just like your CPNM lab, they'll declare some date. Okay, and it's not something that I declare. So your first year coordinator will provide the schedule. This is the date for submission of record. This is the date for conducting the exam. I have to follow that. So that I have to check up with the schedule. But most probably prepare for Monday and Tuesday. Monday submission of record and observation. Tuesday exam. That is how your CPNM course has gone, if I remember. CPNM after your last class, it was Monday, one day for submission of record, and Tuesday was your exam. Okay, so most probably it will be like that. So tomorrow I think is your last session. So tomorrow, but how can I try? Okay, it's not in my hands. Okay, you're in a separate department. You will come to this department in a second year. Till you're in first year, you're under control of a separate authority. The department, we are not in control of any. We are just like guest faculty. Okay. Yes, yes, I know you're writing other labs also. I know that. Mhm. But there's nothing in our hands. Okay. The department, we are guest faculty only. They ask us to take classes. You just take classes and leave. Okay. You're under their control. So whatever days they provide, we have to follow. Okay. So what are the other labs you're writing records? Two labs or three labs? What? How many labs are you writing records for? Three. Okay. Yes, it's difficult, but what can I do? So try to complete. Okay. And what about internal assessment tomorrow that you have to tell me? And if there is no information from your side, okay, tomorrow we'll be having the internal assessment. If you want to postpone, I can postpone only for one day. That is on Sunday. Then you have to. Your Sunday will go. Okay. So it's better you complete. For that we need time to. So what time? For what? Internal exam. Internal exam. The schedule from in the very first day I have to given you the schedule. The very first day I think I know this point will be raising. You should have planned it. Okay. The schedule was released for you on the very first day. I told you. Okay. Isn't it? Is the schedule not given? I think the schedule is already given long time back. Okay. Okay. The very first day I told you. September 4th, there will be an internal assessment. Because the dates we don't control. Okay, so that's the problem. Yes, I know, Malcolm, you have to study, I know. But it's better we complete it as per schedule. Okay, just it's better if you have the internal assessment tomorrow, if you ask me. But if you all want to have it on Sunday, I can do it. That's not a problem. But what you are going to study for one day? Okay, so what you're going to study? Completing course without doing well is nothing, sir. Okay, but then you have to plan it. One day is not going to make a difference. Okay, definitely. Okay. Is everybody on the same page? Is everybody saying we need time, or at least some are ready for tomorrow? Is this the unanimous decision of the class? You need time. Time for what? I'm unable to understand what you need time for. So there are some 8 to 10 programs. What are you going to do in one day? One day, I don't think so it's going to make any difference. In case you have Sunday free, I think you can write records for other subjects. You'll be more free. Why do you want to postpone it to Sunday? I don't know. But in case you want, I'm okay with it. But that's unnecessarily going to eat your time on Sunday. I think it's better to finish it on tomorrow. But that's up to you, okay? That you can discuss in your group and let me know. Okay. But one day I can assure you it's not going to make any difference. If you're not understood what was discussed in the class till now, having one mode of preparation is not going to change anything. And I think most of you will anyway be mugging up the programs. Mugging up the programs, and if I ask you to write a program, if you just by heart it, and that's not going to serve any purpose. Okay. So I don't know. I mean, you want to take time, you take on Sunday, but that's not going to help you. Okay. Or if you want, we can do one more thing. Instead of you writing the programs, we can have like, say for example, 60, say for example 60 students. You can break it up into 10 groups. One group 6 students. 6 students will be given one single program, and then maybe we can discuss it online. Okay, you need not write the program, we can discuss. Okay, we can code it up together. You tell me what to do, I'll write it. Okay, if you get any errors, you just tell me how to correct them. So it will more be a sort of discussion instead of you writing the program and sending me executing. If you want, I can do it that way. Okay, so just to make it clear what I'm saying, we can divide the class into some groups. If there are 10 programs, 10 groups, say in one group 6 students. Okay, those 6 students will be coming online. Okay, will be joining me. I'll be opening up the code window. I'll be typing the code, whatever code you tell me. Okay, so 6 of you will be having more sort of discussion. Okay, so then we'll be explaining you why you're writing each line of code. Okay, so when I ask you what is that line doing, you should be able to tell me. You need not write the entire program. Okay, if you want, you can refer your material and all. Okay, that's not a problem. Don't unnecessarily mug up the program. That's not going to help you. If you want, refer your programs and tell me, but you should be able to explain me what the particular line of code is doing. So if you want it that way, I can do it. Otherwise, the regular way, if you want to write the entire program, execute and submit, that's also fine. So what is the format you want, you should tell me. What is the date you want, you should tell me. Date means only Saturday or Sunday, only those 2 days. Okay. Otherwise, you have to get me the schedule. You have to get me the schedule from your whoever is in charge. Okay. When is the last day? When is the exam? When is the record date? If you can postpone and all these things. Otherwise, tomorrow or Sunday. Okay. So that you can discuss among yourselves and let me know by today evening. Okay. So if there are any doubts regarding the course, so with this you have completed the programs. Okay. If any doubts regarding the course, if you have, you can tell me. Otherwise, we can end the session for today. We're ending it early today. Or if you have any doubts for the internal assessment, if you want to discuss any particular topic, specific doubt, I can do it now. Otherwise, we can end the session. I'll be staying here till 1:30, no problem. If you have any specific doubts, internal assessment, or if some of you want to write the record now, you can go ahead and write the record, complete it, no problem. Any doubts you can ask me. Otherwise, tomorrow 10:40 class will be having the internal assessment. Okay, format you have to tell me. I've given you two options. Just let me know the format you're comfortable with. Okay. So any doubts regarding the internal assessment? What about your other two labs? The two labs, was there any exam planned? Are they given you any date? Or classes are still going on? Okay. Okay, what I will do then I'll just check up with the other faculty to see whether what is the last date and all. But anyway, you should be prepared for either tomorrow or Sunday. Okay. Let me know the date. Let me know the date and the format. Okay. So I'll be waiting for you till evening. Okay. Otherwise, I'll frame the own format and start tomorrow. Okay. If you don't tell me the date or the format, date will be tomorrow. The format will be whatever I decide. Otherwise, you tell me the date and the format. That's up to you. Okay. So you're free to leave now. Those who want to leave, you can write your record. It's not a free time. Okay. You're still in the official time till 1:30. It's better you use it for your record. Record most probably Monday you have to submit. Okay. Don't delay it. Okay. But if you have any doubts, you can ask me. Others can leave. Do you have a class in the afternoon after 1:32? Some class you have? Okay, fine, fine. Then you can proceed for that class. Have your lunch and proceed to the next class. Okay, if you have any doubts, you can definitely ask me. Otherwise, you can leave. Okay.